Thank you very much, ladies and gentlemen. I'm very glad to give some beginning of this major event. Starting in 2020 spring, I was still director of CMSA. I was very happy to see that CMSA was doing great. But that was during the COVID period. I came to China at that time and working in Tsinghua at the same time, still working for Harvard. Everything was in Zoom in those days. So I start to think that we should have a lecture series cooperating between Harvard, CMSA, and Tsinghua together on a series of lectures on literature in the mathematical science. I thought that was really very good. The lecture series will be focused on significant developments in mathematics that have influenced our discipline in all kinds of area, apply or not apply, and also on the lifetime accomplishment of significant scholars all over the world. And I think we have done a great job in the past 5 years, and it's still going on. My directorship was taken over by Dan Free, who has done an excellent job, and I admire him that he was able to do it so well, better than me. And I'm very happy to see that he came up with many excellent candidates to give talks, including the current one, Professor Bridson. And I think this title that he gave is excellent, and I would like to learn more about it. And we are going to have some more significant lecturers, some from China, some from all over the world, which I think is very good to spread around what is modern and what is old in the sense of lifetime accomplishment of significant scholars. And I hope this will go on. And many of our students in China are listening to these lectures, and they will learn from you. And I hope later there will be some of our scholars who will give talks that some of you can learn from here too. So thank you again, Dan. I hope everything goes well. I will be listening, and I will be happy to cooperate in the near future between CMSA and Tsinghua. Thank you.
That's awesome. Thank you to Yao for that introduction. Thank you to Dan for the invitation to talk. Welcome everybody around the world, and the few brave souls who've got up early here in Boston to come and so I have somebody to talk to in the room. So I'm going to talk about profinite rigidity, which I like to think of as chasing finite shadows of infinite groups. And this is very much a colloquium style talk. It starts off gently, and then I hope to get to more or less where we're up to with the state of the art in this subject, and sketch some of the ideas. And please do ask questions either during the talk or at the end. I'll mention a few of the landmarks in the field, and then give some references where you can find out more. And tell you at the end some of the open problems that are the most pressing from my point of view. So I do want to start off gently. Just so before we start talking about profinite rigidity, I just want to talk about groups a little bit and why we study groups. Well, I hope you all know lots of reasons why you study groups. The automorphisms of any object in mathematics form a group. And in that sense, I think of group theory not as a branch of algebra, but just as a branch of mathematics. Just like numbers are everywhere in mathematics, so groups are everywhere in mathematics. Numbers don't belong to the number theorists. They belong to all of us. So we should all be interested in groups. But I really want to talk about finitely presented groups particularly, and we'll talk about why that is. And then the main theme, what I really want to get onto is thinking about the extent to which infinite groups can be captured by understanding their finite images, or if you like, their actions on finite sets. And we'll be particularly interested in groups that arise in geometry, particularly low-dimensional geometry, for example, the symmetries of that tiling of the hyperbolic plane. So I want to start, that's an example I'm going to use. It'll keep coming back throughout the talk. Okay. hyperbolic triangle group. Okay, so how should we? So we're out in the wild trying to understand the automorphisms, the symmetries of things. Say that ethane molecule there. Now, being sophisticated people, you could give me the name of the automorphism group of that. Or if you've never heard of groups, you might just start counting, exploring. A child could explore the symmetries of that object and figure out it's got 6 symmetries. An undergraduate mathematician will learn the name of a group that describes that. But if you're just an honest explorer without the vocabulary of group theory yet, you might start making notes like I've made there. That you figure out it's got 6 symmetries, and you give them names. There's a basic thing you can twist, take hold of the big carbon atom and twist 3 times. You get back to the start. So twisting 3 times is equal to the identity. Or you could flip. You could swap the two carbon atoms. Flip. If you do that twice, that's the same as doing nothing. And if you stare at it for a while, you can figure out if you flip, then twist, then flip, that's the same as if you twisted twice. Okay? So you made some observations, and then you stop making observations. So what have I done? I've said, yeah, there's 6 symmetries, but you only need these 2 basic operations to get them all. The rest are obtained by composing them. And then I've written down some rules I've noticed connecting these basic operations. And that's what we do when we look at the symmetries of something, we stare at it, and we find out there's some basic operations. This comes up all over in mathematics, of course. You've got some complicated thing. So yeah, there's lots of things you could do, but are there some basic elementary moves so that everything I care about can be obtained by doing combinations of these elementary moves? So when you're looking at symmetry, what you want is you want some generators, some hopefully finite list of basic operations that when you compose them, you get everything. Then you start writing down some rules, some relations, and then you stop. Okay, so what do I mean when I say a group is given by a presentation? So you're asserting 3 things. First, the blue assertion that these basic operations really are enough, that every element of the group can be obtained by doing a suitable composition of these elementary operations. Second, that these relations, these rules are really true, right? That on the previous slide, it really is true that if you F then T then F, that's the same as doing T twice, right? Those rules actually have to be true. And then the third, why do we stop? Why do we close that bracket? Because that's all the information you need to understand the group. Right? The claim is that everything else, all relations between the generators, can be derived as direct consequences of the ones that I've given you. And what's the consequence? Well, they should be obvious consequences. So what's obvious? If R equals S and T equals U, then RT is the same as SU. And if doing some combination of the generators, some relator is 1, well, if you do A, then you do nothing, then you undo A, that's the same as doing nothing. So those are obvious consequences. And to say that a group has that presentation means that all relations involving generators can be derived from the given ones. Right, so that's as with so much of undergraduate mathematics, we package it up quickly and give it to students as something about quotients of free groups. But this really is, we describe groups like this because when you're out hunting in nature, that's the way you see symmetries of things. So, for example, the hyperbolic triangle group, so the color preserving, orientation preserving symmetries, that tiling, you want to prove that really is a proper description of that group. You have to convince yourself of 3 things. There's 3 basic operations, A, B, and C, so every symmetry can be obtained by composing them, that they satisfy these rules, and that every product of the basic generators that equals the identity can be deduced just from these rules. And in this case, A, B, and C, just pick your favorite triangle, say that one. And A is rotation about that vertex, B is rotation about that vertex, C is rotation about that vertex. And then you have the exercise to prove that really is a proper description of all the symmetries of that picture. Right, very good. Okay, so we've got our language that we're going to study finitely presented groups, and the groups that arise as nice fundamental groups, for example, in geometry and topology, if the fundamental group's compact objects, they'll always be finitely presented. But not every group that you encounter in life is going to be finitely presented, sadly. First of all, I'm only talking about discrete groups, right? So I'm not talking about Lie groups I'm not talking about Lie groups and similar things. I'm only talking about discrete groups, so all the groups will be countable. But even amongst countable groups, you can't always expect to get finite presentation. So, for example, take the additive group of rationals. That's not even finitely generated, right? That's an easy exercise. What requires more thought, and if you've never done this for yourself, I recommend it as an exercise. Pick a group that's finitely generated but can't be finitely presented and try and prove it. That's actually a little bit tricky, right? That actually does lead you to real mathematics to think about that. But they're not exotic monsters, which is the point of this simple example here. I want to convince you that there's lots of groups that arise in nature that are finitely generated, but they don't have any finite presentation. So here's two 2x2 integer matrices, invertible 2x2 matrices, elements of SL2Z. And then I position the X, Y, and Z as shown there to get three 4x4 matrices. Not a complicated thing, not a monster. But I tell you, I promise you, that the subgroup of SL4Z generated, sorry, I forgot where I was, SL4Z generated by those three matrices does not have finite presentation. Okay? So that is to say, you start writing down rules that, okay, this product of A, B, and C is equal to the identity. And you keep writing rules, and at no point in this process will you be able to deduce everything that's true just from a finite set of rules that you've written. That,
do X and Y generate a free group?
X and Y do generate a free group. Yeah, that's why it's a 2 rather than a 1 in that matrix. Yeah, yeah. So yeah, that's the point. Secretly, I'm saying something about a direct product of 2 free groups. But I don't know an entirely elementary proof of this. One needs some theory to see that group doesn't have a finite presentation. An easier way of seeing, an easier but less instructive way of seeing that lots of groups don't have finite presentations is that one convince oneself that there are uncountably many non-isomorphic finitely generated groups, but there's obviously only countably many finite presentations and therefore only countably many finitely presented groups. But I prefer this, right? That groups that arise in nature, you shouldn't necessarily assume they can be finitely presented. And in fact, it's very hard to see when groups are finitely presented. And it's very hard to find finite presentations. And when people say things like that, you think of dusty old men sitting in offices proving that something's reducible to a Turing machine of some sort. This is much more concrete than that, right? So Sarah advertised this question a lot. Take a very sort of as concrete a group as you could wish for, SL3Z. And, the group 3x3 integer matrices, 7 and 1. Can every finitely generated subgroup of SL3Z be finitely presented? Okay. Now, I showed you on the previous slide that in SL4Z, you can find finitely generated subgroups that have no finite presentation. Can you do that in SL3Z? We don't know, okay? Which is sort of in some way embarrassing and in some way enlightening. It just shows how we go through life assuming we understand basic objects like SL3Z. We really don't understand the subgroups of SL3Z. Okay, that's really the key point here. So in particular, we don't know if all the finite generated subgroups are finitely presented. So that's a very concrete instance that we just don't know there, but ultimately, hopefully, we will know, right? On the other hand, if you go to objects that are a little bit bigger, then you can start proving one can never know. So we already saw on the previous slide that SL4Z harbors difficult finitely generated subgroups. And in fact, one can prove that there does not exist an algorithm. So here we just haven't found out the truth yet. Here, this is a statement about the truth being hard, right? That does not exist, there cannot exist an algorithm that given 12 4x4 integer matrices can determine whether or not the group that they're generated is finitely presentable or not. Okay, so here you really are going to encode something undecidable, something that indirectly it'll come down to the halting problem for Turing machines that you really cannot decide, given 12 4x4 integer matrices, whether they generate a finite presentable group or not. Now, often when you have undecidability theorems, it's something about not knowing where to look. But here, the difficulty is more subtle. Now, this theorem is quite a bit harder than this one. But it's also true that if you give me a finite subset of SLDZ, and D has to be bigger than 4 now, and you promise me that the finite group of matrices, finite set of matrices you've given me, generate a finite presentable group. So there is a finite presentation. There's still no algorithm to find it. Right? So even if you know it exists, you can't necessarily find it. Okay, well, that's all very depressing. So the theme is, right, so hard things and undecidable things are very close at hand when you start thinking about groups. They're not, you can build monstrous constructions, but I'm not building monstrous constructions. I'm working with 4x4 matrices. Okay, this is, and here's another illustration of this, the fact that hardness is close at hand. So I could just tell you it's very hard to extract information from a finite presentation, or I could show you an example. Here is a very small example. So here are 3 groups. G1's missing for a reason I won't go into. So the first group, generated by 2 elements, A and B, and it's only got one rule, that the B conjugates A to A squared, which I've written BA as A squared B. G3 looks like G2. So again, B conjugates A to A squared, C conjugates B to B squared, A conjugates C to C squared. I just gone around a cycle of 3 doing the same thing, or I could go around in a cycle of length 4. Right, so these groups look pretty similar, right, deliberately. Small presentations. Can we understand them? Well, one of these groups is infinite. In fact, it has infinitely many finite quotients. One of these groups is an infinite group that has no finite quotients. So you can't get it, it's an infinite group, but you can't get it to act on any finite set. One of these groups is the trivial group. That is to say, the only group that has elements satisfying the given rules is the trivial group. Okay, which one's which? Well, you stare at that for a minute. Okay. I used to take votes on this, and almost always there's an equal vote at some point. We'll come back to that, okay? Now, so instead of just staring at presentations, how we really understand groups, well, we don't study groups because some nasty algebra teacher told us we had to go and study groups. We study groups because we care about them, because we find them in nature, because they're automorphisms of things. So instead of just staring at an algebraic description of a group, what you really want to do is get it to act on something. Okay? But somebody hands you a group, like one of those on the previous slide, and you don't know anything about it yet. So what are you going to get it to act on? Right, well, sort of historically, people have tried to get groups to act on vector spaces. That's representation theory, right? How do you represent a group as a group of matrices or a group of linear transformations? Or you might, the most primitive objects, after all, are finite sets. So might you be able to get your group to act on a finite set? It's much better if you can get your group to act on something that's geometrically or analytically interesting and use the structure, the geometry, the topology, or the analytic structure of this thing you're acting on to illuminate the nature of the group. And there's a canonical way of doing this. Oh, sorry, there's one canonical thing at least that you can do to get every finite presented group to act in an interesting way on something. And that is you build a space whose fundamental group is the group you gave me, and then you have an action. You have the action of the fundamental group on the universal cover. And this is a perfectly straightforward algorithmic thing to do. So you give me a finite presentation, say that presentation there, and instead of regarding it as an algebraic object, I regard it as instructions for building a topological space. Take one vertex, take one generator for one loop for each generator, and I attach a 2-cell according to the instruction you gave me that AB should be equal to BA. Okay? And then the magic of algebraic topology says, oh, the fundamental group acts on the universal cover. So instead of just sitting there saying, you can't understand me, the group now starts acting on something. It's acting, it's a nice discrete group automorphisms of the universal cover. Okay, now it won't always be a manifold when you do that, but you can do it for any finite presentation. I did it for Z cross C, but given any finite presentation, I could follow the same recipe, and I could build a compact, finite, two-dimensional complex whose fundamental group is the group you gave me, and then it's acting on something. It's acting on the universal cover. Now, we like manifolds better than we like cell complexes. So how do we turn this into a manifold? Well, just as you can embed any graph in R3, pretty obviously, you can embed any finite two complex in R5 because you have enough room. So if you just take a generic map, if you're in R4, then two-dimensional cells might meet in a zero-dimensional intersection that you can't get rid of perturbing. But if you're in dimension 5, then you have enough room to push the two cells off each other. So it's easy to see that you can embed any finite two complex in R5. Then you just fatten it up. You just take an epsilon neighborhood of it, take the boundary of that epsilon neighborhood. That will be a closed, right, closed four-dimensional manifold. And that, the fundamental group of that closed four-dimensional manifold will be the group you started with. So this is a proof that every finitely presented group is actually the fundamental group of a closed four-dimensional manifold. And or five-dimensional manifold or six-dimensional manifold. Starting in dimension 4, you can realize any finite presented group is the fundamental group of closed manifold. And therefore, you can use manifold topology and geometry to study your groups. You might, this argument sort of also picks out special classes of groups. You can do a fancier version of this that tells you every finite presented group is the fundamental group of a closed symplectic manifold. You can prove that every finite presented group is the fundamental group of a closed complex manifold. But you can't get symplectic and complex structure at the same time. You can't make every group the fundamental group of a closed scalar manifold, for example. Right? And therefore, it points you towards special classes of groups. Which are the finite presented groups that arise as fundamental groups of compact Kähler manifolds? With that same thought of which classes of groups emerge as special, the most obvious one here is three-dimensional manifold groups. Right? We said every finitely presented group arises as a fundamental group of a closed four-manifold, but three-manifold groups are special. Right? So we already see that here, and that's going to be a big theme. Okay? Fundamental groups of closed three-manifolds have many properties that generic groups don't have. Okay, now, so the first person to think sort of in these terms about groups was Max Dehn, who wrote this sequence of very important papers between about 1905 and 1912. There he is. Picture of him at the time. And in particular, he was the first to realize this thing we were just talking about, that it's very hard to extract the information from a group presentation. And so he asked various questions, but in particular, and this was before the word algorithm was widely used, if or was used at all, of course, but he was really asking, in the same way that Hilbert had been asking certain algorithmic questions without actually saying algorithm, Dehn picked that up. Do there exist algorithms that allow us to answer basic questions such as, is the given group trivial? Is a certain product of the generators, a certain word in the generators, is that a consequence of the given relations? And he wasn't just interested in doing algebra. Crucially, what Dehn was really interested in this time was classifying structures in low-dimensional geometry and topology. And so this is the key sentence for me in that paper. One has already led to such problems by necessity when working in geometry and topology. Knotted space curves, in order to be completely understood, demand their solution. So what Dehn was actually doing, his main occupation at that time was trying to classify knots, right? Trying to extend the known knot tables, try and prove things like the fundamental group of a knot is Z if and only if the knot is trivial. That was his real focus. And at some point, like many people in history, he thought, oh, I've reduced that to algebra. Right? Only the trouble is the problem to which he'd reduced it was at least as hard as the problem he'd started with. And then he realized that and articulated these problems in group theory. Now, in the end, and we see three manifolds being special, it took the whole of the 20th century, but for the groups that Dehn was interested in, all of the groups that arise in knot theory or more generally three-dimensional topology, there do exist algorithms to solve the fundamental problems he was interested in. Okay? If you've got a group that's the fundamental group for compact three-manifold, you can answer questions like, if I know the group is the fundamental group for compact three-manifold, I can decide if it's trivial. If you give me a product of the generators, I can decide if that's the identity or not. If you give me two words in the generators, I can decide if those are conjugate elements or not, which corresponds to free homotopy of loops in three-manifold. So all of those problems that are for the groups that arise in 2 and 3 dimensions, they're all solvable by complicated algorithms, right? That you need the whole of the geometrization program to solve them. For finitely presented groups in general, these problems are famously undecidable. And this was really the achievement mainly of the Russian school in the middle of the 20th century, in the 1950s. So there is no algorithm that, given a finitely presented group, can decide if it's trivial or decide if two given groups are isomorphic, etc. So in 3 dimensions, algorithms exist. In 4 dimensions and higher, algorithms don't exist. And given this close connection between group presentations and manifolds, you can use that to prove that there's no algorithm to decide homeomorphism between, say, triangulated manifolds 1 through dimension 4 and above. Right? That's not an obvious reduction to group theory, but there is a reduction that exists. So if we can classify 3 manifolds, we can never classify 4 manifolds. Right. Let's go back to our 3 groups, just as an exercise. Now, the first one's the easiest group, right? That's fairly easy to see. That's infinite. And you can get it to act on lots of things. You can write down 2 matrices, A and B, that satisfy those relations. So here we're doing representation theory. We understand our group by writing down a faithful linear representation of it. You can get it to act on lots of other things. For example, here's a way it acts on the line by affine transformations. It also has lots of finite quotients, right? So I deliberately wrote the presentation of the ethane molecule in a way that shows you that this group, this infinite group, acts on this finite object. And what it amounts to is adding that you make the generator A have order 3 and the generator B have order 2. So that's a finite image. So it's got faithful linear representations. It's got affine representations. It has lots of finite quotients. How about those other 2 groups I showed you? One of them's infinite, but it's an infinite group that has no finite images. It also has no matrix representations over any field in finite dimensions. So one of those groups is infinite, one is finite, one is trivial. Okay, if it's got no linear representations, you can search forever for matrices satisfying the relations. You won't find them. Okay? You can try and get it to act on a finite set forever. You'll never find one. How the hell are you going to prove the group is non-trivial? Well, you have to get it to act somewhere, right? And the answer is, and this is an insight sort of Higman, but then picked out by Sayre, is that the group that's non-trivial acts nicely on a tree. And it has a geometric action on a nice contractible one-dimensional object, a tree. At this point, if we had a larger audience in the room, I'd get you to vote. Well, we'll have a quick vote anyway, but you've only got 3 seconds to decide. Who thinks G3 is the trivial group? Who thinks G4 is the trivial group? Right, that, for those of you who are online, that was more or less equal votes. It's always like that. I know no good reason to prefer one group over the other. In fact, G3 is trivial and G4 is an infinite group. Right, now don't despair. There's nothing algorithmic you could have done to answer that question. Because in fact, you can prove, myself and Wilton proved, there's no algorithm that, given a finite presentation of a group, will decide whether or not it has a finite quotient. You can't figure out the finite quotients of a finite presented group in general. There's also no algorithm that, given a finite presentation of a group, will decide whether or not the group has any finite dimensional linear representation over a fixed field or over any field. Okay. Now, how do you prove such a theorem? That's what I want to dwell on. There's obviously going to be, you're going to prove an undecidability result. So at some point, you'll reduce it to some known undecidability problem. There'll be some reduction to a halting problem for a Turing machine that might go through various other encodings. In this case, it goes through the encoding of something called the universal theory of finite group, which Slobodskoy worked on in the 80s. But the reason this theorem wasn't proved until 2015 is it also relies heavily on modern technology that's less obviously relevant, and that is the geometry of non-positively curved and hyperbolic spaces. Okay? In particular, cat-zero cube complexes and ideas of John Stallings, Donny Wise, and many other people. So I don't have time to go into that here, but I want to show this picture. Fix this in your mind, that the theorem is just a theorem about groups. Okay? It's a theorem about the non-existence of algorithms for finite presented groups. It's proved using the geometry of non-positively curved singular spaces of non-positive curvature and hyperbolic spaces. Spaces where you see this sort of geometry. Okay? Right. So things are hard. Things are generally impossible. They're not impossible in low dimensions. And even to prove basic theorems at finite presented groups, we find ourselves using a lot of modern machinery about groups acting on spaces that are hyperbolic or non-positively curved. Again, I say that this, I'll only take a minute. This is a bit of a tangent, but again, I want to emphasize that these undecidability and hardness results, they're not about terrible, monstrous constructions. They're not about pathologies that you deliberately build. You find them in really hard, concrete places where you care about answers. So, for example, if you've got a finite presented group, you might say, well, I'll ask my computer or my AI assistant to find out a finite dimensional representation of a finite field for me. So, can you decide if a group has a representation into SL3 over some finite field, for example? The answer there is yes. Okay? If you ask, can I decide if my group has a representation into SLN, where I'll let n vary, but I'll fix the field, say the field with 7 elements, then the answer is no. Right? So that's what's written here. If you fix n and vary the field, then you can decide if your finite presented group has, let's say, a surjective representation and map onto SLNQ. If you fix your field and vary the size of the matrices, you can't. And the key difference there is that if you fix the size of the matrices, then you have a nice group scheme. You start doing algebraic geometry or model theory based on algebraic geometry. And you're asking about the existence of FQ points in some variety. Right? So you then can start, let's say, using things like Langevin estimates and things from number theory to prove that exact algorithms do exist. So, but again, concrete groups, the things we care about are happening in concrete groups where we have. Right, now. So that was all about groups, why we care, how hard life seems to be, but we're not giving up. We're going to go and try and study profinite rigidity. Okay, so given a group, we want to try and understand it via its finite quotients. We've just seen that without further conditions, we can't even decide what the finite quotients of a group are. Okay, so we're going to have to think carefully about what groups we want to study. But nevertheless, you've got a group. You don't know what to do with it. What are you going to do? Well, you could try and represent it somewhere or look at its finite quotients. Just try and do something to gather some understanding. And what we want to know is when can one expect to be successful? Right? This is profinite rigidity. When can you recognize what your group is just by understanding all of its finite manifestations, all of the ways it can act on finite objects, all of its finite quotients. On the two pictures there, that's Fritz Grunewald on the left, who first got me interested in this for a reason that will come up in a minute. And on the right, Alan Reed, my long-term collaborator with whom I've been working on profinite rigidity. Right. Now I realize, as I was saying, that this is a literature seminar, and there's very little literature that I've talked about. I've mentioned some famous problems. I haven't given you the citations. There are 2 pieces of literature here that have all the citations you'll need for everything I say today. First of all, there's a very nice seminar Bourbaki by Bertrand Rémy in the spring of 2024 that's just appeared in the printed form. That has a very nice exposition of these ideas and very many references. And then I've just been looking at the galley proofs of this article, which was my talk to the European Congress, also in 2024. And again, that has lots of references. So those are two good places to chase down these ideas and references to them. Now, we've been discussing that some groups, that have interesting groups, they might not have any finite quotients, right? Or you might not be able to find what the finite quotients are. So if we're going to try and understand groups completely by understanding their actions on finite objects, by understanding their finite images, we'd better restrict our attention to groups where at least there's a chance of understanding everything about the group. So a minimum requirement should be that the group is residually finite. So whenever, say, somebody says a group is residually something, it means every element survives in a quotient, which is the second adjective. So a group is residually finite if every non-trivial element of the group survives in some finite quotient. Right? If you're going to understand the group, you've got to see which elements are not the identity. So a minimal requirement should be at least every group should survive, every element of the group should survive in some finite quotient. So we're going to restrict our attention to residually finite groups. I'm hesitating there because you've got to absorb that definition. Every element, non-trivial element of the group, remains non-trivial in some finite quotient. Okay, you might say, well, that's not good mathematics. You've just made a definition that says, yeah, I need this to get going. But thankfully, lots of groups that arise in nature are known to be residually finite. It's quite easy to see that all finitely generated matrix groups over any field are residually finite. To prove that, it's just a slightly fancier version of, well, why is SLNZ residually finite? Well, if you give me an element of SLNZ, I just reduce mod P for some prime that's bigger than every entry in your matrix, and your favorite matrix is still clearly alive in SLNZ mod P. Just a slightly fancier version will show you that actually every finitely generated linear group is residually finite. Okay? A harder fact is that all fundamental groups of three manifolds, all the groups that arise in three-dimensional topology, are residually finite. Again, that relies on Thurston's geometrization conjecture. It's also true that if you write down a random group with a reasonable model of what it means for a presentation to be random, that you just fix the generators and pick some relations at random according to a certain regime. If you do that in a reasonable way, you'll find that random groups are residually finite. That's quite an indirect argument, nevertheless it's true. So lots of the groups that arise in nature, and in particular in low dimensions, are residually finite. So our basic question should be, you've got a residually finite group, so you know that every element of the group survives in some finite quotient, so every finite subset of the group survives in some finite quotient. Is that enough to figure out what the group is, or to tell lots of things about the group? Right? So that's the basic question. If you've got a residually finite group, to what extent can you understand the group by just looking at its set of finite homomorphic images? So we'll be looking for profinite invariants of groups, and I'll explain in a second why I'm using the word profinite. So that's an invariant of the group that you can see in its set of finite quotients. And then we'll be interested in profinite rigidity. That's a question like, if two groups have the same finite quotients, do the groups have to be the same? Or at least how similar do they have to be? Can you actually deduce they're the same? And two- and three-dimensional manifolds will come up a lot. We'll return to this point about finite presented groups and finite generated groups being different, that we'll see that things are wilder for finite generated groups than they are for finite presented groups. And hyperbolic geometry, which already appeared a couple of times, will appear again. Right? Hyperbolic geometry is good for you. It helps you in almost everything in life. And to keep things concrete, this group that we started with are the groups we love, our favorite groups determined by their finite images. If I go out into the streets of Boston and find a residually finite group in the gutter and realize somehow that it has exactly the same finite quotients as this beautiful group, when I clean up that group I found in the gutter, will it be isomorphic to this group or not? Right? So you have some finitely presented group, you just found it in the gutter, has the same finite images as this group. Is it that group, or is it some imposter? Right. Now, the word profinite's getting used here, profinite rigidity. In my experience, telling people in a lecture like this what a profinite group is doesn't really help, because either they know or the definition passes you by. Once you've heard it a few times, it's one of those things that becomes very natural after a while, but it takes a while. In this setting, I'm talking about profinite completion. So you got your finite generator group, nice discrete group gamma, say Z, and then you look at all the finite images of it. That's what we're interested in. But these finite images, they're not just a set of groups that you throw in a big bucket. They order themselves naturally into a directed system. Because if I take a finite quotient of my group and then take a finite quotient of that, then there's an obvious direction. So the finite quotients of a fixed group gamma form a directed system. So it's a directed system of finite groups. Finite groups with the natural topology are compact. So if I take the inverse limit of a system of compact objects, I get a compact object. And that is what the profinite completion of the group is, right? So you look at all the finite quotients, they form a directed system, you take the inverse limit, that'll give you a compact group, which is called gamma hat. Now, so you start with something like Z, Z hat it's profinite completion. That'll be an uncountable group. It's an uncountable compact group. Now, you might say that's a stupid thing to do. You took a nice countable thing like Z and you traded it in for an uncountable thing. Yeah, but you do that when you pass from the rationals to the reals. There are reasons for completing things, right? So, and what you gain in this case, crucially, is that it's a compact topological group. So there's a natural map from gamma to gamma hat. So an element, give me an element gamma, it lies in each element of the directed system. So you get a map from gamma to the inverse limit, gamma hat. That will be injective if and only if gamma is residually finite. So you should think of gamma hat as really taking a completion. That gamma is a subgroup of this compact group, gamma hat, and you've really completed it in the way you complete the rationals to get the reals, for example. And it's a totally functorial construction. And there's a deep theorem of Nicklock and Siegel I'm going to use without further comment that telling me I don't have to worry about what I mean when I talk about isomorphism. Okay, so any talk on profinite groups or profinite rigidity, you have to say what a profinite group is. But now you're not going to have to remember it, because what I was talking about previously was just trying to understand a group by understanding its set of finite images. Right? So the finite images of gamma just take all the finite groups onto which gamma acts. Now, there's a theorem that was proved by various people in the 1980s independently. If two finitely generated groups have the same set of finite quotients, then their system of finite quotients is the same in this more sophisticated sense of having the same profinite completion. Right? That has some content to it. From right to left is more or less just the universal property. From left to right requires some argument. Right? It's not obvious that just because you have the same set of finite quotients, you have the same profinite completion. But in fact, you do. So for example, you can't have two different finite generated groups, so they've got the same set of finite quotients, but this one maps onto the symmetric group of S6 in 17 ways, and this one maps 13 ways. Right? They actually, if you have the same set of finite quotients, not even counting multiplicity, you have the same profinite completion. So you really have this correspondence, complete correspondence between how you can map onto finite groups. And therefore, in what follows, when I write something like gamma 1 hat is isomorphic to gamma 2 hat, you can just read that as saying gamma 1 and gamma 2 have the same set of finite quotients. Okay? And that's how I'll pronounce it. Right. So the basic question we're interested in is absolute profinite rigidity. A finite generated group is profinitely rigid in the absolute sense. If given any other finitely generated residually finite group that you find in the gutters of Boston. If it has the same finite quotients as my lovely group gamma, then it's actually isomorphic to my lovely group gamma. That's what we'd like to recognize. Can we find profinitely rigid groups? Well, we don't have to look far to find one. It's not hard to convince yourself that if you've got a residually finite group, finite generated residually finite group with the same finite quotients as z to the r, then your group actually has to be z to the r. And I'm going to quickly whiz this, the only proof. We're going to have a quick proof of this because the structure of the proof is not hard, but it sort of it illustrates some nice idea. Okay, so you got this group you found in the gutter. Oh no, the group in the gutter is now gamma. That's unfortunate. It's got the same finite quotients as z to the r. Well, first of all, you observe that this group you found outside actually has to be abelian. Because if it wasn't abelian, then the commutator of some commutator, the commutator of two elements, would be non-trivial. But then that element has to survive in some finite quotient, which means gamma would have some non-abelian finite quotient. But it can't, because it's supposed to have the same finite quotients as z to the r. Okay, so that was easy. It's abelian. And then, once you're in abelian groups, well, we know what finite generated abelian groups look like. And so then we can figure out that they give me two different ones. They'll have different quotients. So the key step is that the mystery one, the one you found in the gutter, you had an argument to see it was abelian, and then you know what you use about abelian groups. Okay. Now, you could do that for other group laws, like nilpotent of class C, right? So nilpotent of class C means you take brackets more often than just 2 brackets equals 1. You could do the same argument that says you find a group in the gutter that has the same finite quotients as a nilpotent group, then that group that you found will have to be nilpotent of the same class. And then you can start using structure theory about nilpotent groups. If you do that, you'll find that take your favorite nilpotent group, there'll only be finitely many other groups that have the same profinite completion. But according to which group you take, then it might not be unique. Okay, that some nilpotent groups are profinitely rigid, some aren't. And there's some nice arithmetic that comes in there. Okay. Now, reflecting on that argument, we had this first step to say you just find this mystery group that you find outside. We proved it was abelian, and then we know what we use what we know about abelian groups. So what we did is we started with an absolute profinite problem, deciding if a group is absolutely profinitely rigid, and because we had a group law, we could immediately reduce to a relative problem. So a relative profinite rigidity problem would be, you say, instead of thinking about all groups, I just think about this nice class of groups, say fundamental groups of compact Kähler manifolds. I take 2 groups from that class, and I ask if those groups have the same finite quotients, will they be isomorphic? And you can see that's an easier sort of problem, because then you're going to use all the structure in whatever context you're working to solve that problem. And correspondingly, there's been a lot of literature in recent years about relative profinite rigidity problems, okay, where you put yourself in a nice class of groups and you use what you know about that class of groups, their geometry or whatever, to answer the question of which ones have the same finite quotients. It's much harder to do an absolute profinite rigidity problem where you just find a group in the gutter and you have to prove that it's in your class before you can start using what you know about groups in your class. There's a third type of rigidity problem, profinite rigidity problem, which has been solved, which has been considered, sorry. And for sort of 30 years or so, this was really the main, more than 30 years, this was the main one that was considered. And it was proposed by Grothendieck in his penultimate published paper in 1970. So what Grothendieck was interested in was a profinite rigidity question where instead of just having 2 groups, right? So in absolute profinite rigidity, you give me 2 groups, you tell me they have the same finite quotients, and I've got to see if they're isomorphic. Now, one of the difficulties of that problem is I have no map to compare the first group to the second. What Grothendieck was interested in, for reasons I'll explain in a minute, is a situation where you actually do have a map between the discrete groups. So you've got a map, which you might as well assume is injective, that's an easy reduction, from one discrete group to the other. And it's this map which matches up their finite quotients. Okay, so you're mapping P to gamma. So you've got a finite quotient of gamma. You obviously get a finite quotient of P. And so what you're interested in is when that map gives you an isomorphism of profinite completions, which says two things. First of all, you map P to gamma. We go down to a finite quotient of gamma. Then P has to map onto that finite quotient. It has to fill it up, so you can't tell it isn't the whole gamma. And every finite quotient of P has to arise in this way. There are no other exotic ones. So you say that a group gamma is Grothendieck rigid if that never happens. If you take a finite generated group injecting to it, then it won't be true. That, in other words, if the injection gives you an isomorphism of profinite completions, that only happens in the trivial case. That is to say, with the original map of discrete groups was an isomorphism. Now, why was he interested in that? Oh, okay, I'll tell you in a minute why he's interested in that. First, I want to scare you a bit more, okay? I want to scare you a bit more by just saying profinite rigidity is not something you should expect to see all the time. So we saw it for free abelian groups. If you go just a tiny step away from abelian groups, so here's two groups, G1 and G2, I've called them, that each have a cyclic subgroup of index 25. Right? So they're just a little cyclic group for 25 acted on by Z. Acted on in two different ways. In the first case, the Z acts as multiplication by 6. In the second case, the Z acts as multiplication by 11. What matters here is 11 is 6 squared mod 25. Those groups are not isomorphic. You can do that on the back of an envelope going home on the bus, except nobody has envelopes anymore. But you can do it on the bus anyway. You can convince yourself those groups aren't the same. And if your bus journey is long enough, you'll probably be able to convince yourself. But those groups have the same finite quotients. Okay? So as soon as you move a little bit away from abelian groups, you lose profinite rigidity. Now, Baumslag wrote those examples down, but he was really abstracting the essence of a beautiful little paper that Serre wrote in 1964. And I want to mention this because, again, it brings out the role that arithmetic plays in profinite rigidity. It's hidden in the statements, but it's very much in the proofs. So what Serre did is he took a smooth projective for a certain smooth projective variety defined over a number field, and he extended scalars in two different ways. Right? Took two different embeddings, necessarily Galois conjugate embeddings of this number field into C. So then he took the smooth projective varieties you got by those extension of scalars. Right? So the underlying scheme is the same, but the topological manifolds he wanted to prove were not homeomorphic. And the way he did that is he calculated their fundamental groups and proved that they weren't homeomorphic. But because the underlying scheme is the same, the algebraic fundamental group, the étale fundamental group is the same. And so that is the profinite completion of the topological fundamental group. So we had these two non-homeomorphic manifolds. The fundamental groups were different, but their profinite completions are the same. Okay? And that's a crucial idea. It's abstracted algebraically in these little examples of Baumslag, but this idea of using Galois conjugates to construct things that are not profinitely rigid is something that's come up a lot in recent years. And it really goes back to this paper of Serre. Okay, that was a little. Let me go back to Grothendieck. Okay, so going from 1964 to 1970, why was Grothendieck interested in this rigidity question? Well, it's in this paper from 1970, and he proved the following beautiful theorem. So he was interested at this time. He was trying to do Tanaka duality for discrete groups. So he's trying to recover a group from its representation theory, just as we're trying to recover a group from its finite images. Okay? And what he proved is sort of connecting these two problems of recovering a group from its finite images or recovering it from its representation theory. What he proved is this theorem there. To take any commutative ring, non-zero commutative ring, could be Z or could be Z mod 2. If you've got a homomorphism of discrete groups, gamma 1 and gamma 2, that will induce an equivalence of categories the representation theory over this ring, by which I mean finitely presented modules with a group action, that the map that discrete homomorphism will induce on categories will be an equivalence of categories. Well, it will obviously be an equivalence of categories if the original map was an isomorphism, and that's what he would like to do, to have an easy form of Tanaka duality. But what he proved is if and only if the induced map of profinite completions is an isomorphism. Okay? So his problem of trying to recover a group from representation theory, he's reduced to a problem of profinite rigidity. This map that you hoped would be an isomorphism between discrete groups, what you've got is that actually the map it induces on profinite completions is an isomorphism. And so he naturally asked, well, can I get where I want from this? If you've got two finitely presented groups that are residually finite, and you've got a map between them that induces an isomorphism of profinite completions, does that only happen in the trivial way? Does that only happen if the original map between the discrete groups was itself an isomorphism? Okay, now people worked on this and there's various positive and negative results, but it was finally settled by myself and Fritz Grunewald, whose picture I showed you earlier. That's why I got interested in this subject in 2006. And the hope, so it's a hope, the answer is no. In fact, so again, there's some hyperbolic geometry involved here. You can construct Gromov hyperbolic groups, and you can realize them as groups of integer matrices. So you can construct a hyperbolic subgroup of SLNZ and a finitely presented subgroup of its direct product, so that the inclusion map induces an isomorphism of profinite completions, even though the subgroup is a subgroup of infinite index. And in fact, it's not abstractly isomorphic to the direct product either. Okay? So the answer to Grothendieck's question is no. And again, I want to emphasize it uses hyperbolic geometry in the proof. Now, in the interest of time, I'm going to, so again, non-positive curvature in the background, arithmetic is in the background. I'm going to skip over the outline of the proof and come back to our search for absolute profinite rigidity. Okay? Now, so a lot of the results have sort of been negative, saying that actually things can go wrong. And all I've actually shown you in the positive direction is z to the n, which isn't very impressive. And so you might start wondering, well, are there any interesting examples of profinite rigidity? So you got this group, you got this nice group, gamma, that you love, and then you find this group, lambda, lying in the street, and they're residually finite, they have the same finite quotients. You want to know, can I ever conclude that this mystery group that I found is indeed the group I want, gamma? Now, we want to avoid arguments like the proof I sketched for z to the r. You want to avoid situations where you have a group law that reduces it to a relative problem. Right? There are theorems like that, but that's not so interesting. What you want, if you're going to prove a good theorem, you want to really attack the essence of trying to solve absolute profinite rigidity sort of in the wild. So you want to think about full-size groups, that is, groups that don't satisfy any group law. And the easiest way to do that, the full-size, grown-up, proper, respectable groups should have a non-abelian free subgroup. That's sort of a proper grown-up group, full octane, alcohol allowed. So what we're really asking is, are there any full-sized finitely generated groups that are profinitely rigid? And this problem had been open for a long time. Where should we look? Well, I've sort of been dropping heavy hints. The world of general groups, this isn't going to happen. This seems to be a rare phenomenon. What about if we go to three-manifold groups? And hyperbolic geometry, which has been quoted so often so far, maybe we'll use that again. So we're going to look in three-manifold groups and see, can we understand profinite rigidity for three-manifold groups? Now, the way I've said that could be interpreted as sort of, I'll just being a scaredy cat, I'll only ever think about three-manifold groups, and I'll try and decide which ones are profinite equivalent. But I really want to say, I want theorems that say two things. I want to understand the extent to which three manifolds are determined by their profinite completion within the class, but I also want theorems that say if you find a group out in the wild that has the same profinite completion as my three-manifold group, then that mystery thing has to be a three-manifold group. And when I say three manifolds, also two manifolds, so our friend there will come back in as well. Now, what are we going to use about three manifolds? Well, they're special. I've mentioned a few times Thurston's geometrization program. So what was Thurston's vision? Thurston's vision was that every compact three manifold can be cut up into geometric pieces, these locally homogeneous manifolds. That cutting up procedure, so you cut up along a canonical system of embedded spheres and tori, and annuli if you have boundary. And then the pieces should have complete metrics that are locally homogeneous, modeled on one of the 8 geometries that arise in dimension 3. So there's Poincaré on the left, who sort of got this going, Thurston in the middle, and then Perelman on the right, who of course proved Thurston's geometrization conjecture, says the vision's correct, and therefore we can list. There's an algorithm that will give you a complete list of all compact three manifolds. We understand their fundamental groups, they're residually finite in particular. Now, the theme that's emerged in the last 10 years is that many properties of a three manifold, not just the three manifold group, but the three manifold of itself, can be detected in the profinite completion of the fundamental group. Okay? There's lots of themes like that. You want to ask me questions, I'll give you examples, but that's the theme. Okay, a great deal of the information about a three manifold is encoded in the profinite completion of its fundamental group. Right, now a generic three manifold will have a hyperbolic structure. And so those are the ones where we'll be most concerned with. Not all three manifolds are hyperbolic. You also have Seifert-fibered spaces, three manifolds which can be foliated by circles. We'll also be thinking about those. Now, first of all, some bad news. Oh dear. Right, can you see that on the big? Oh, you can see it on the big screen. There's lots of positive results. As I was saying, there's this theme that lots of information can be recovered from the profinite completion of pi 1, but not everything is good. So one way of building a three manifold is to take a surface bundle over a circle. Right? You just take a compact surface, whip it around the circle, and glue it back to itself with some holonomial map. If your surface is just a torus, and you take a generic element, a hyperbolic element of SL2Z, the mapping class group of the torus, then that bundle that you get will have solved geometry. It will be a lattice in the three-dimensional Lie group solve. So here's two hyperbolic matrices. I take the torus bundles over the circle corresponding to them. They just glue top to bottom with that map. If you do it with these two particular matrices here, you'll get three closed three-dimensional manifolds that are different. They're not homeomorphic. In fact, their fundamental groups are not the same, but their profinite completions are the same. And again, this is encoding a little bit of arithmetic. Those two matrices are not conjugate in SL2Z, but they are conjugate in SL2 of Z mod M for every M. It's a little bit of class field theory there. Okay, so we can't expect a theorem that says whenever a profinite rigidity theorem for all three manifold groups. It's just not true. But remember, hyperbolic geometry is good for you. So maybe if we stick to hyperbolic geometry, we will be able to prove a positive theorem. And so that's this theorem, which is, I'll dwell on for a minute, because this is the answer to the question, do there exist full-size groups which are profinitely rigid? So here there's a finite list of hyperbolic three manifolds. I'll describe a couple of them in more detail in a second, but there's a finite list of them so that each of them is profinitely rigid in the absolute sense. So if you take the fundamental group of one of these three manifolds that I'm going to describe, and you find some other group that has nothing to do with three manifolds, but it's residually finite, and it has the same finite quotients as this group, then actually it magically turns out it has to be isomorphic to this three manifold group. And what are these examples? Well, the easiest ones to explain are, first of all, there's the Weeks manifold, which is, so by Mostow rigidity, the volume of a three-manifold with hyperbolic structure is an invariant of, it's invariant to the homeomorphism type of the manifold, or even the fundamental group of the manifold. The Weeks manifold is the smallest volume closed hyperbolic three-manifold. That is distinguished from all other finitely generated groups just by its profinite completion, just by its set of finite quotients. The same is true of the unique non-uniform lattice of minimal co-volume in hyperbolic three space, which is a group I'll describe to you in a second. And again, there's some arithmetic here that the Bianchi group, the PSL2 of Z extended by a cube root of unity, that is also profinitely rigid in the absolute sense. It's distinguished from all other finite generated groups by its finite quotients. And what is this unique, the unique non-uniform lattice of minimal co-volume? This is a very beautiful object. You're all familiar with how to triangulate the hyperbolic plane with ideal triangles. In much the same way, you can triangulate a hyperbolic three space with ideal tetrahedra, but you have to insist they're regular ideal tetrahedra. All the dihedral angles are pi over 3. And just as you could take that middle triangle there and start reflecting in its sides to generate the tessellation, so you could take a regular ideal tetrahedron and start reflecting it in its sides, and you tessellate the whole of the free space. So that gives you a quotient. If you take the quotient by that group, the group of symmetries, that triangulation, you'll get a manifold. But there's actually something that's a bit smaller, in that just as you can take a Euclidean tetrahedron and divide it up into 24 congruent subtetrahedra, you could do exactly the same in hyperbolic space. So instead of tessellating hyperbolic three space by reflecting the sides of that, you subdivide it into this 1/24th and you reflect in the sides of that. And then one can prove that that's the smallest hyperbolic orbifold non-uniform, smallest non-uniform lattice. It's the smallest non-compact three-dimensional hyperbolic orbifold. And that's the presentation of the group there. And that is uniquely distinguished from all other finite generated groups just by its finite set of quotients. Okay, now, I don't have time to go into the proof, but there's sort of been hints of it all the way along. There's arithmetic here. It's the arithmetic of the so-called trace field. You have to understand characters of representations into SL2. There's various three-dimensional stuff, Mostow rigidity, compact cores, a bit of knot theory, and crucially, this work of Agol following the work of Danny Wise about groups acting on cube complexes, and which Agol used to solve the virtually Harkin conjecture. Now, I realized I've run out of time. Let me just tell you. Okay. Our friend that we've had with us throughout this lecture, is that distinguished from all of the finitely generated groups by its profinite completion? Yes, of course it is, or I wouldn't have shown it to you so many times. In fact, there's a list of, that's 12 Fuchsian groups, 12 Fuchsian triangle groups, all of which are profinitely rigid in the absolute sense. Again, there's some number theory here. What's crucial is that they're similar to a group of norm 1 elements in maximal order and a quaternion algebra over a real quadratic field with certain properties. The key thing is that the invariant trace field of these groups has some nice arithmetic. And let me focus on what I've written at the bottom. We've discovered some profinite rigidity, but there should be a lot more. So far, we've got finite lists of Fuchsian and Kleinian groups which are profinitely rigid in the absolute sense. A reasonable conjecture would be that they all are. Right? That you can distinguish any hyperbolic three-manifold group or hyperbolic two-manifold group from all other finite generated groups just by looking at finite quotients. That's the conjecture, but we can only prove it for finitely many things so far. Seifert-Fibert spaces, we also have theorems for, and crucially, this theorem, so I should say 2026, it just appeared. I made a big deal at the beginning about a difference between finitely presented and finitely generated groups. Using the structure of certain Seifert-Fibert spaces, what this theorem here says is that there exist three-manifold groups. So if you take the direct product of this three-manifold group with itself, it's profinite rigid in the sense that it can be distinguished from all other finitely presented groups by its finite quotients, but there exist infinitely many finitely generated non-isomorphic groups that have the same finite quotients. So finiteness properties, the difference between finite generation and finite presentation, can be made to play a crucial difference here. There are groups which are uniquely defined amongst all finitely presented groups by their finite quotients, but not among all finitely generated groups. And I'll leave you with some conjectures or open questions. I haven't mentioned the free group. I mentioned the free abelian group. You might think I could tell you as an exercise, oh, if you've got a group that's got the same finite quotients as a free group, then it has to be a free group. That's an open question. It seems to be a very hard open question where there's a lot of activity. Okay? So there's things like a free group. This triangle group, for example, it's not so far from a free group. Now, a free group is also a lattice in SL2R, but we don't know if finite generated free groups are profinitely rigid. We suspect that all lattices in PSL2R and PSL2C, including the free group, are profinitely rigid, but we don't know. A direct product of two free groups is not profinitely rigid amongst finitely generated groups. That's an old construction that's related to this problem of Grothendieck. But we suspect, or I suspect, that it is profinitely rigid among all finitely presented groups. And again, the state of our ignorance, I can't resist always coming back to SLNZ. Is SLNZ, say SL3Z, profinitely rigid? If you have a residually finite group with the same finite quotients as SL3Z, is your mystery group SL3Z? That progress has been made on that question, and it really brings us back to this question of Serre that I advertised, 1974 question of Serre. We don't understand the subgroups of SL3Z. And so in particular, could it be that there's one of these Grothendieck pairs, that there's some finitely generated subgroup of SL3Z so that the inclusion map induces an isomorphism of profinite completions? We don't know. And then you can ask about your favorite class of groups. Are they profinitely rigid? Okay, thank you.